All right, so there's our problem. There's our statement. What do we want to do? Okay, so Maple, as I said, is a symbolic solver. It is capable of taking expressions, solving them symbolically. You get back an equation as opposed to like a number, right? You get back an equation that that follows some requirements that you have. What you need to, there's a few commands that you really need to know with Maple. Like these are the basics to do anything. There's obviously a ton of other stuff that goes with it, and you can usually Google a lot of that stuff or look at the documentation as you get into it. But I just wanted to go through this really quickly so you guys all have an idea. All right, the first thing that you want to know is you can take differentials, or you can take derivatives of expressions. So this first one, diff, you just say diff and then the expression that you want to evaluate and then the variable that you're evaluating it with respect to. You can solve differential equations. So you have something like the line up on top. Maybe you want to solve that equation for t. You can use the dsolve command. You can evaluate expressions at certain values. So we want to evaluate our boundary conditions at some r. You do that with the eval command. Solve will solve a set of algebraic equations, and then subs will replace certain things with other things in equations. So maybe it's better just to show you how this looks. Let's go over to Maple here. All right. Everybody can see that okay? Can you see it okay in the back? More or less? Okay. A couple things. When you're using Maple, so I find it's best to work in this worksheet mode. So worksheet mode has just the code and then the resulting, the computations that come out. If you work in document mode, it's trying to be like a word processor, and I find it kind of annoying. So worksheet mode is how I would recommend doing it. If you want to add comments, like non-evaluated stuff to your code, you can do that by going to a line where this little cursor prompt is and hit Control-Shift-K, and that'll add a comment above the thing that you're trying to write. If you want a new command line, it's Control-K. And if you want to delete a line, it's Control-Delete. All right, so that's, first of all, how you do that with shortcuts. You can also like right-click and do stuff with your mouse, but again, I find that a little slow. Okay, so let's go for this specific problem. Let's go through how we would solve it, pose it in Maple, solve it, and apply the boundary conditions. All right. So the first thing you're going to do is we want to make sure that our command or our workspace is pretty clear, like there's no residual stuff from other worksheets. So we'll say restart. Right, and then you type the command, and you follow the command with a semicolon. If there's any command that you want to issue that you don't want to see the output, maybe it's like a page of output or something, you can put a colon, and that will suppress output. Right. So we hit restart, and now it's cleared our workspace, and we're ready to go. All right, so the first thing that we want to do is let's write out our equation. So we had, let's start with the ODE in Q dot, which was what, dq dr equals 0. So how do we write that in Maple? Well, that's going to be diff. That's our differential command. We're taking the differential of r times t of r with respect to r. All right, so r times t of r with respect to r. Note that t is a function of r because I've said t parentheses r. Right? That's indicating that t depends on r. And Maple needs to know that, otherwise it's going to think t is a constant. So there's a functional relationship there. So first let's see how this looks. Okay. So I've typed this in. It has interpreted what I have to say as this, right, which is an equivalent way of writing that derivative. Just use the chain rule. Okay, so that's fine. We want this to be equal to 0. So again, I do that. Now, in subsequent calculations, I want to be able to reference this thing, right? I want to be able to reference this result. So I need to name it something. I need to call it something so I can easily refer to it. So I'm going to go back up here. I'm going to call this, excuse me, I'm going to call this ODE. So, excuse me. So for ODE, to assign a name to something, the way to do that is colon equals together like that. And so ODE is going to be the name I give to that stuff. Anytime I use that in the future, it will just substitute in the stuff for the name. All right. Let's see. So I have that ODE. We're not quite right on the ODE because it should be the second derivative. So let me let's take the second derivative. So we need to take the differential again of what? So differential of, see, I had this kind of wrong, didn't I? R times the differential. Okay, everybody see what I did there? So I had it kind of wrong to begin with, which is fine. But now I'm taking the differential of R times dt dr. Right? That I've fixed it to be our actual ODE. And I have to take the differential again with respect to R. OK. So this should be the equivalent of that ODE as we've written it. OK, now I want to solve this ODE. We did this by, let's see. So we did this by substituting in a rate equation and all that, and then integrating. We can just use the dsolve command here to do that. So dsolve is our solver for differential equations. So dsolve of ODE. And it already knows there's only one thing that's a functional relationship in here. It's t as a function of r. So it's already going to be able to automatically detect to solve this for t as a function of r. If you have something more complicated, you might specify, so it's dsolve ODE, comma, the thing you want to solve for. But here it should be just fine. All right, so I dsolve, and now it solves the equation, just like that, right? It's super easy. So this, being a trivial example, is maybe not obvious like how this helps. For the homework, you're going to do this. You're going to be solving, well, for A homework, you'll be doing this. I don't think this current. There's maybe homework 3, you'll be doing some Maple stuff, maybe homework 2. Those equations aren't so nice, okay? And you'll be happy that you know what you're doing in Maple, okay? So we have our general temperature solution. Again, I want to name this something. So let's call this, what do I call it here? TS. All right, so my temperature solution, TS, is going to be dsolve ODE. So okay, now it's named that. The next thing we need to do then is enforce boundary conditions. So we need to first state what the boundary conditions are in Maple, and then substitute in our equation. So let's go with the first boundary condition. Let's see, BC1. Call it BC1. And that's going to be what? So we have our temperature solution. We said TS is equal to T, let's call it TH, right? TH is some constant. We'll tell it later what that is. So this is sort of right, but not quite. We have to evaluate TS at some specific position R. This is just saying the general solution is equal to TH. It's not quite right. So we need to go back and use that eval command. So eval. So we're going to evaluate TS at R equals R in. Okay? So we evaluate TS at R equals R in. And that's equal to TH. One other problem, though. This TS includes both the left-hand side and the right. It's the entire expression. We only want to say the right-hand side is equal to TH, right? So we need to specify that we only want to evaluate the right-hand side of TS and then evaluate that at Rn. So to do that, we use the command RHS of TS. Right, sorry for making you guys erase, but OK, so we're evaluating the right-hand side of TS at R equals Rn and assigning that to be equal to TH. We're saying that it is equal. So hopefully I've got everything here. OK. OK, so we do that. Now we're seeing that our boundary condition 1 is exactly what we expect. It's the C2 plus C1, right? It's the same thing that we wrote out by hand. OK. Any questions on this so far? OK. Seems pretty straightforward, but I think once you guys start typing, you'll have questions, right? So let's do the same thing for the second boundary condition, eval RHS. of TS at R equals R out, and that's equal to TC. So now we have two boundary conditions. The next thing is we need to solve for C1 and C2. Right? We didn't get that far by hand. We just left it off at these. But let's actually use Maple to solve. All right, so the way to do that is we have this command called solve. And the arguments of solve are going to be the equations that we want to solve and then the unknowns that we're solving for. The way that you specify more than one equation is using the curly braces. Right? So you have we have a curly braces here for the equations that we're going to solve, and then we have a second set of curly braces that's going to contain the constants or the variables that we want to solve for. Okay, so let's see. We are solving for BC1. We're solving for BC1, comma BC2, and the unknowns are C1 and C2. Note that the underscore is there. The default for like a constant of integration in Maple is to put the underscore in front of the constant number. You do have to include that. If you try to take the results here and copy it to ease, which you probably will want to do at some point, ease does not allow you to start a variable with underscore. Okay, so you'll have to maybe copy it in and then do a find or search replace for all underscore C to C underscore. There's a little bit of cleanup that you have to do, but it should work. Okay, so we solved this. Hopefully it works. Yeah. All right, so we now have solved our system of equations for C1 and C2. And you want to stop here and look at this, right? You don't just take this stuff blindly. Stop and look at it to see if it makes sense, if you're seeing any variables. Like if you looked in here and you saw there was still an R present, that's wrong, right? You know there should not be any R left. If there's a T present or T is a function of R, that's wrong. So you need to just make sure at this point that everything makes sense and it aligns with what you would expect. Okay. I'm going to call this, let's call this stuff constants. So we can keep track of those. So now we've got our constants of integration. And we can go back and let's update our solution TS to actually sub in these constants into the expression. All right, so we'll use the same name, TS, and we're just going to replace it with our new with our new assignment. So we'll say TS is equal to the command is called subs. Right, subs is going to take some set of equations and then apply that to another set of equations. So here we're going to say I'm subbing in my constants. And what am I subbing it into? I'm subbing it into the original TS above. If I do that, now I see the actual general solution. And now I have T as a function of R. I've got my constants appearing. I have a functional dependence on R, right? So this all sort of makes sense, right? The things that we expect to be there are there. Functional dependence on R, and the constants appear where they should. All right, so we could just take this. At this point, you could just actually take this and copy it, put it in ease, tell it what T, C, T, H, and the other geometry are, and have your solution. Right? This will solve the problem. Let's see. Before we do that, let's compute a couple other things here, because I want to show you how to use this this simplify command. So you guys all, or hopefully mostly, remember thermal resistances. We'll be talking about that now, after we finish this topic. Thermal resistances are a way of describing the impedance between two temperatures, right? The impedance of heat flow between two temperatures. So let's use this expression to calculate a thermal resistance that corresponds to this problem. And we should see something familiar appear. So let's say we want to compute the cylindrical resistance, or cylindrical coordinate resistance, for this this equation, which is TH minus TC over Q dot, right? Just we're using the definition of resistance, which a little ahead of myself here, but this equation just comes from Q dot equals TH minus TC over R cylinder. That's fine, but we actually need to tell it what Q dot is first. So I'm going to use my little Control K shortcut and insert something here. And let's put in an equation for Q dot. So Q dot is going to be what? So just Fourier's law, which is minus 2 times the area 2 times pi times R times L times K times the differential of T as a function of, let's see, how do we do that? T is the differential of TS, right? TS with respect to R. So why did I do that? So we have our general solution. We have our specific solution now, this TS. Right? We have this solution. We want to take the derivative of this and then use that to calculate Fourier's law. So I'm using the actual solution TS there. Again, though, I only want the right-hand side. So I need to go back and say right-hand side of TS. Right? There's my Fourier's law applied to this problem. All right, now I can compute the cylindrical resistance, and that's there. That sort of looks familiar, but it's not quite like what you're used to seeing, right? If you go to a resistance formula table, it's not quite right. So let's use the command simplify. I'm going to simplify our cylinder, and hopefully we see something pretty familiar, right? So if you look at a cylindrical resistance table, remember what the resistance is. It's what? Ln of R out over Rn, which is exactly the same thing as Ln of R out minus Rn, right? If you're subtracting two logs, it's actually the division of them, over 2 pi Lk, right? There's our resistance. So by taking our cylindrical coordinates, enforcing temperature boundary conditions, and then computing, using Fourier's law to compute heat transfer, we now have found the cylindrical resistance formula for this geometry. Okay? And it was super easy with Maple because you don't have to do any algebra or calculus. Any questions on that? Yeah?
Is like the unsimplified version useful? How it doesn't simplify on its own?
Yeah, I mean it's right. It's just verbose, right? It's saying exactly the same thing but with a bunch of extra terms. So these two things are equivalent mathematically, but it's just simplifying it. At least the final result, you probably want to at least attempt to simplify it because it'll just make it more concise. Yeah. Anything else? Okay. Very good. Okay, so that's Maple. Again, as you get into this, look at the example. There's an example in the Lecture 2. This example is in Lecture 2 folder. If you have questions, I'd say come to office hours. We can talk about the software tools. I'm not an expert in Maple. I just know how to do kind of the basic stuff. But yeah, it's a really powerful tool that I think you'll be well served to use. OK, back to this.